All right, second session. And we look at another full wave rectifier. And this time the full wave rectifier is going to be a bridge rectifier. So center tap rectifiers are not, well, they're not popular anymore. There's no reason for us to use them. Previously, when we needed an adapter, let's say with variable voltage output, so you'd have 1.5 volts, 3 volts, 4.5, 6, 9, 12, 15, 18 volts. You'd have a transformer with multiple taps in the coil, in the secondary coil. And so each output would give you a different voltage. And they could turn a switch, like a mechanical dial switch, that would just connect the voltage that you would require to the diode circuit. Okay, now there are far better ways of obtaining a variable value. And they all begin with this bridge rectifier circuit. Okay, so come on, where is the share button? There we go. Okay, bridge rectifier circuit works pretty much the same as a center tap, but it requires 4 diodes instead of 2. And both diodes are going to conduct, not both diodes, sorry, 2 diodes are on at a time and 2 diodes are off. And again, let me draw out the circuit. So the way I always remember the circuit is 2 arrows pointing up and 2 arrows pointing down. So you have 2 diodes pointing up this way, and the other side, you'd have 2 diodes pointing down. Okay. And if you look at this bridge configuration, there are 2 terminals where you have 2 anodes connected together, and there are 2 terminals where you have 2 cathodes connected together. And those are right here. 2 anodes and 2 cathodes connected together. That is where you would connect your load. Okay. So whatever load you have will be connected between these terminals. And that's what this indicates. I typically am not that big a fan of drawing a circuit like this. This is how, of course, we would draw it for, technical stuff. But for explanation purposes, the circuit that I drew on the right, that makes a whole lot more sense. Okay. So again, 2 diodes pointing up, 2 diodes pointing down. There is an interface where there's a node where 2 anodes are connected together, and there is a node where the 2 cathodes are connected together. And those terminals are where you would connect your load resistor. And then the other 2 is where you would connect your AC source. And the AC source could be a transformer, could be wall outlet, could be anything. Okay. So this time, let me follow the same notations. We have A and B pointing down, C and D pointing up. Take a pause while students are drawing it out. Okay. All right. So let's see what happens in the positive half cycle. Positive half cycle, we have a plus up top, minus at the bottom. If you look at the nodes, let me go ahead and label the nodes. So starting from the top, let's call this node 1, node 2, node 3, and node 4. So positive half cycle, positive terminal is connected to node 1, and negative to node 3. If we look at the diodes, we can see the anode of diode A would be plus, and the cathode of diode B would be minus. Then the cathode of diode C is plus, and the anode of diode D is minus. In this circuit, in this explanation, plus and minus simply refers to which end of the diode is higher or lower. Okay, which end of the diode is higher or lower. So in the positive half cycle, the anodes of the anode of A and the anode of C are both connected to the positive end. So for diodes A and diodes B, we can see that they would be forward bias. If they are forward bias, current would flow in this direction. Does that make sense? Let's take a pause while you think over that. And so it results in plus minus. Any questions? In the negative half cycle, you now have plus at the bottom and minus up top. This connects positive end of the diode D and the cathode of diode B higher. Then C is here, it's negative, and A is negative. And if that's the case, then diodes D and C are on, they're forward bias, and diodes B and A are reverse bias. And so current now flows in this direction. Again, it results in the current flowing in the exact same direction for both half cycles. And both half cycles are now flowing the resistor or the load the exact same direction. The resulting voltage is VL or V out of D. The graph that we obtain would be exactly the same as this one. Okay, so this is full wave, meaning both half cycles are rectified into the same direction because the current is flowing in the same direction for both half cycles. Let's take a pause. If you have any questions. Does that make sense? Right. Yes, go ahead. Yes, so all this, the question being asked is about ground in a circuit. So ignore the ground for now. Let's not insert the whole, it's a whole different discussion. But as far as this circuit is concerned, or any circuit is concerned, it simply means you're taking all the terminals that have the same notation and they're connected together. That's what it would mean in a circuit. And then you connect it to ground, whether it's a floating ground or whether it is connected to the chassis of the instrument or actually connected to an electrical ground outside the building. Let's keep that discussion on the side. As far as the circuit is concerned, it means that all endpoints or all nodes with this ground symbol are connected together. And that's why I stated I prefer to have this diagram. Anyway, other questions? The average value of this waveform is also 0.637 because we are taking both half cycles and averaging it out. Okay. The obvious disadvantage is that in real life, you have two diodes. In a center tap, you have one diode. So you would need at least one diode forward drop or one diode drop of voltage before it can turn on. So if you apply 10 volts to these diodes, then 0.7 volts of that 10 volts is used to turn on the diodes. In a bridge rectifier, there are two diodes in the path, meaning if you apply 10 volts, then 1.4 volts are required to turn on the diodes. Okay. So 2 times 0.7 volts required to turn on diodes, which is, by itself, it's not a big deal. If you wished output of 10 volts, you would apply 11.4 volts or 11.5 volts, slightly larger, enough to compensate for the voltage that is required to turn on the diodes. Okay. But this is not what we need, right? That output is not what we need. And so, let me see. Our output is still AC. The value is still fluctuating. And so we put a capacitor in parallel with the resistor, and we call it a filtering or smoothing capacitor. It filters the output voltage to provide a near constant flat line, depending on the values, of course. So it is known as a filtering or smoothing capacitor. So this shows you a half-wave rectified output. Okay, half-wave rectified output. If we connect a capacitor across that load resistor, what happens? Well, in the positive half cycle, capacitor, let's assume capacitor did not have any charge. So we'll ignore this. Capacitor starts charging. It charges, goes up to here. Negative half cycle, diode turns off. When the diode turns off, again, let me draw the circuit here. So you have a half-wave rectifier, you have a resistor, or that's the load resistor. Let's put a capacitor in parallel with that load resistor. Positive half cycle, current flows through, goes here, goes here. Don't worry about transients. If you remember from 201, capacitor will take some time to charge up. But eventually it will reach full charge depending on the size of the capacitor. Once it reaches full charge, it's going to have some voltage across it. Negative half cycle, diode turns off. If it turns off, remember, natural response, stored energy of a capacitor or inductor is discharged through a resistor. Chapter 4 from 201. So diode on, diode off, circuit is disconnected. Capacitor now discharges through that resistor. This is plus, this is minus. It's supplying energy. Electrons are flowing in their direction. The resistor will still have voltage. That discharging waveform, depending on the size of the capacitor, if it's a huge capacitor, it's a big capacitor like 1,000 microfarads or 10,000 microfarads, it is a huge bucket and you have a small tap. So it releases the energy at a very slow rate. And that is what is indicated by here. So this is the discharging of the capacitor of C, natural response. How many of you remember that from 201? It's 201 a long time ago. So this point is the step response, capacitor charging, and when the diode is off, it's the natural response, capacitor is discharging. It discharges, the voltage across that resistor is still in that same direction because now the capacitor is acting like a energy source. Goes from minus to plus, discharges through the resistor. And then before it can discharge completely, the next half cycle appears and it starts charging again. And then it turns off, starts discharging. And so that cycle continues. Okay, that cycle continues. And if you look at this waveform in isolation, it looks like this. So you have T, and your waveform, your AC waveform is now rectified. So you see something like this. And so on and so forth. If this was your original output, which was about, let's say 10 volts. So this is V out as a function of time. And this is obviously not to scale. This portion is almost like a flat line, but there are waves, ripples, and hence this is known as an electrical ripple. And this ripple typically is in the order of like 0.1 or 0.15 volts. And again, that is just a random value. So it could be 100, 150 millivolts, or even less than that. A physical analogy can be made as, let's say, you have a 5-gallon water jug. There's a small tap at the bottom. You have this big opening at the top. You fill up the water at the top and you take water out at the bottom, small tap. 5-gallon water jug, the neck of the jug is big. You turn on the tap to fill it at the top. At the bottom, it's going to come out very, very slowly. Does that make sense? Hopefully, like a physical analogy. So if the size of the capacitor, size of the bucket, or the size of the jug is large, it takes a very long time for it to empty out. The smaller the bucket or smaller the jug, the faster it would empty out. If you have a 1-gallon water jug versus a 5-gallon water jug, 1 gallon would empty out faster. Make sense? So in a filtering capacitor, the larger the capacitance, the slower it would discharge, the flatter your line, and the smaller your ripple. Did all of that make sense? Hopefully. Let's take a pause and think on that, and let me know if you have any questions. Any questions? Okay, no questions. Then let's move forward. Okay, so a couple of equations regarding the half-wave and full-wave rectifiers. Full-wave rectifiers, of course, it's going to be higher because instead of a blank in the middle, you'd have another cycle to charge the capacitor. Okay, so before the capacitor can even discharge to a lower level, the next positive half cycle hits and it starts charging again. So the average value of the waveform would be much higher. So there are a couple of derivations in there, but if you are an engineer who's designing a system, you would want to pick a value of a capacitor. So the equations for picking the value of the capacitor are given here. This would be the load current IL, right? IL over V. And then you have the time period of the AC waveform, that is T. And then VR is the ripple, the desired ripple. So means if you wish to design a system and the system requires that you would need a ripple voltage less than 100 millivolts, then you would plug that into this equation, plug in the time period. The time period would pretty much be an AC wall outlet would be 60 hertz, unless you're using a different kind of system. And so that is fixed. And then IL is the load current that is desired in the system. Okay, so the desired load current, the desired ripple, and then the known time period, then you can calculate what kind of capacitance value you would need to apply in that system. Typically, most rectifiers are full wave rectifiers. It's been a long time since I've actually seen a half wave rectifier. The most cheapest ones that I'd seen was like a transformer with a diode just, twisted into the coil. No circuit board, nothing. So cheapest devices are usually like that. They save money wherever they can. And so you'd have a diode, you had a capacitor connected, and they just twisted the leads together and put a bit of solder on it to hold the bond, and that's it. But I haven't seen one of those in a long time. Okay. So even with this, sometimes, not sometimes, often that is, yes, go ahead. Question? That's on the system. That's basically, so the question being asked is how would we know the value of VR? And that's where the requirement comes in. It's not that we know what it is. We want to keep it lower than some value. So let's say you have a system where you already know that your system is sensitive. You would want the ripple to be like 10 millivolts or less, perhaps. And so we are working backwards. We are doing a design of a system based on the output we want. So in this case, VR is not a input, VR is the output. And we'd want the VR value to be within a certain tolerance. Make sense? Yeah. That's where the value would come from. So this would be mostly for like design of a system. Okay. So typically this is not the end of the rectifier circuit. We'd still want some sort of regulation to take place for an even flatter line, because the resulting voltage that we obtain here is not usually at a level that we want, right? If we want 5 volts DC, which is the standard USB spec, anytime you plug in your wall charger, you plug it into a computer, USB specification states it cannot be more than 5 volts. Now you have USB-C and power delivery, and that's completely different. But a standard USB port is never more than 5 volts. Okay. At the most, it could be 5.1, 5.2, but not more than that. So if we want 5 volts, for instance, at our output, then our transformer probably needs to be at least, and I'm talking about this portion right here, should be at least 7 volts or higher at a minimum. Okay. Because if you have a full wave rectifier, 1.4 volts goes into turning on 2 diodes. So 7 minus 1.4 gives us what, 5.6. So we are already down to 5.6 at the output of the bridge rectifier. Then we have a current limiting resistor that would eat up some of the voltage. Then you have the capacitor, and then you have thermal losses that would occur. And so the final voltage we obtain might be closer to 5 volts. We still don't know. So again, working backwards, if you want V out to be 5 volts, we would work backwards. And working backwards means going in this direction. If you want 5 volts there, we would add maybe, I don't know, 100 millivolt ripple. That would give me 5.1 before the capacitor. And then add the resistor. Let's say the resistor drops some voltage across it, maybe another 100 millivolts. So at this point, before the resistor, I would need 5.2 volts. Let's say the 100 millivolts over there. Then the bridge rectifier requires 1.4 volts to turn on both diodes. And you add 1.4 to 5.2, gives you 6.6 at the input. And so maybe a safe bet is, instead of using 6.6, we use 7 volts. And so finally, we would say perhaps apply 7 volts from the source. So we'd work backwards from our desired output. Does that make sense? Right? And so if you're trying 7 volts, perhaps at the output, we might get V out as equal to, let's see. So you have 0.4 volts. So you might get 5.4 volts for a V in of 7 volts. Does that make sense? But our goal is to obtain 5 volts. Our goal is to obtain 5 volts. But because we are applying 7 volts at the input, we are obtaining 5.4 and not 5. So it is not at a level that we need for our system. Okay. And what we do then is we use a voltage regulator. A regulator, by its name suggests, it regulates the voltage to a desired level. It regulates the voltage to a desired level, and it provides a constant output voltage at the terminals. Okay. Make sense? Any questions? Let's see how much time. 36. Still have time. Okay. And the diode that would allow us to do that kind of regulation is the Zener diode. Okay, Zener diode. Go back to last class. Remember, we talked about a diode that operates specifically in the reverse breakdown region, because in the reverse region, once the depletion region width increases and is overcome due to the external electric field that is applied, a huge amount of carriers will now cross the junction. And because they are crashing through the junction, the amount of energy that is transferred is a near constant. So it's a huge amount of current flowing through with a very near constant output voltage. Okay, that voltage is known as the Zener voltage. Remember, reverse breakdown occurs due to two different mechanisms. One is the Zener breakdown, the other one is the avalanche breakdown. But all diodes that are engineered to work in reverse bias are called as Zener diodes, irrespective of whether it is actually Zener mechanism or whether it is avalanche mechanism. Okay, all diodes that work in the reverse bias are known as Zener diodes. Okay, and Zener diodes basically have a characteristic that looks like this. In a forward bias, it works as a normal diode, but it would be overkill to use a Zener diode because Zener diodes would be slightly more expensive than a regular diode. Okay, so if you just need to use a diode in forward bias, we would not use a Zener. But nevertheless, it is still a diode, so it still functions as a regular diode in the forward bias. But this is where the magic happens. Zener diodes are exclusively used in reverse bias. They are engineered to work in the Zener breakdown region right here. And this is, again, a little bit exaggerated curve. It is even more, I would say, like this, and perhaps like this. So the curve is even more flatter and steeper than what you see in the characteristic right there. In actual life, when you connect a Zener diode to your circuit, it will be a near constant voltage. So this is voltage, right? And this is current I. So a huge amount of current is now flowing through the Zener diode, but the voltage across the diode is near constant. It's near constant. And that's where we actually use it. Okay, this is the representation of a Zener diode. If this is the anode and this is the cathode, in forward bias, it behaves as a forward bias diode, which has some diode resistance, and this is the diode forward voltage drop. Forward voltage drop, which if it's made out of silicon would be 0.6 to 0.7 volts, pretty standard. And then reverse bias, it again works like a diode in the forward bias, but it has a Zener resistance and it has a Zener voltage. This Zener voltage is the breakdown voltage of that Zener diode. It is part of the specification of the diode itself. Okay, so let's take a pause. You think over all of that, and you let me know if you have any questions.
Professor, does the VZ almost act like a battery? Or am I interpreting that wrong?
Yes, yes, almost like a battery, yes.
And that's just to kind of make up for the loss. So
Yeah.
you can
Well,
have constant voltage.
it's not a battery like that, but it's like that would be the voltage that would be required to turn on the diode. So yeah, okay. No, I misunderstood your question.
So it removes the cutoff of the.
Yeah, exactly. That is the voltage that is required to turn on the diode. So let me write it over there. So VZ is the turn on voltage. This circuit diagram itself is an illustration of how a Zener diode would work in both forward bias and reverse bias. That's what it is showing. So in the forward bias, the Zener in both directions, the Zener diode is represented as a forward bias diode. Okay, I'll repeat again. In this illustration, in this figure, it is showing you one Zener diode. Okay, one Zener diode. But it is showing you the equivalent circuit of the Zener diode in both forward bias and reverse bias. So in the forward bias, it behaves like a diode. In reverse bias, also it behaves like a diode. And in both cases, the diodes are forward bias, and it requires these voltages to turn on. So Zener can get a little confusing when we first learn about it. So let's take a pause. Let's take a longer pause. Think on that and let me know if you have any questions. And once again, I'll repeat. Sometimes it can get very confusing and harder if we try to understand the physics of things versus just considering as a component off the shelf. Okay, so if you try to look at the physics of things, we are talking about the depletion region that is widening. We have charge carriers, holes and electrons on either side. Depletion region is widening, meaning the border separation is increasing between the junction, but at some point, the external energy, the external electric field imparts so much energy to the charge carriers, they just crash through the junction. That is the breakdown voltage, and that is VZ. That is part of the semiconductor physics of things. And when you look at it as a component, then we simply look at a diode and we say, you apply voltage 0.6 volts in the forward bias, the diode turns on. And then in the reverse bias, you apply 5 volts or 6 volts, whatever the VZ might be, and the diode turns on. So it functions as a forward bias diode in both directions. The difference would be the turn on voltage. Questions? Did all of that make sense? Students are still thinking, okay. Any questions? Billy, you had a question? Oh, okay, just stand. The symbol is very similar to the regular diode, except the cathode is illustrated by a couple of whiskers at the end in the shape of a Z. So you have a triangle, and you have the cathode. And I'm going to exaggerate this a little bit, make it a bit longer. It has little whiskers at the end in the shape of a Z. So this is still the cathode. This is still the anode. Okay, arrowhead pointing towards. But Zener diodes are exclusively used in reverse bias mode. And so the way we would use it as a regulator is we would connect it to a circuit. Let's say you have a supply voltage. That voltage, for instance, let's say it's 7 volts. Okay, as an example. 7 volts. And our Zener diode is rated for VZ is equal to 5 volts. So anytime you connect a Zener diode, it'll always be connected in reverse. Otherwise, if you connect it in forward bias, it is simply a forward bias diode, right? No special thing about it. You connect it in reverse bias, meaning the cathode is connected to the positive end of the supply and anode is connected to the negative end. So Zener diode is reverse bias. Simply put, no matter what input you give, the output of the diode is held constant at 5 volts. Okay, so this would be equal to VZ. V out would be equal to VD, the diode voltage, and the diode voltage in this case is the Zener voltage, which for our example would be 5 volts. No matter what the input is, obviously within reason, ideal Zener diodes, you apply 1000 volts to it, it would still give you 5 volts output. In real life, if you apply 1000 volts to a Zener, it's going to blow up, obviously. But within reason, right? 10 volts, 15 volts, and it's part of the spec, power handling capability, meaning if a Zener diode can handle about 1 watt or 10 watts of power, you could probably apply 10 volts, 15 volts, 20 volts, and the output, the diode would still work. Output would remain constant. The only thing that would increase would be the current that is flowing through the Zener, hence the power dissipation. Let me go back one slide. We saw this, right? So this is the Zener voltage and the Zener current. As you increase the input voltage, the Zener diode current will keep on increasing, but it will keep the voltage across its terminals constant at VZ. At some point, that current would exceed the power handling capability of the Zener diode, and then it gets really, really hot and it will blow up, right? That's what would happen. So again, power of the Zener diode and the voltage of the Zener diode is part of the specification of the Zener diode. PZ is the maximum power the Zener diode can dissipate without breaking, without just blowing up. And VZ, of course, is the voltage of the Zener diode. So in this circuit, we can write an equation, apply KVL. You have 3 voltages. You have the supply voltage, you have the resistor voltage, and you have the diode voltage. So supply voltage is equal to the resistor voltage plus the diode voltage. And similar to a diode load line analysis, we can plot the load line for the Zener diode also. The big difference is that it is plotted in the 3rd quadrant. And because this is because the diode is connected in reverse bias. If we refer to diode voltage, we always take the reference as positive towards the anode and negative towards the cathode. So cathode, anode. Anode is always positive, cathode is always negative. That's why we have V out as minus VD. And then minus simply indicates it's reverse bias. So let's take a pause, think over all of that. Let me know if you have questions before I go into the load line analysis. All right, questions? No questions? Yeah. Okay, so one point about this circuit before I go to the load line analysis is that if VSS, the supply voltage, is less than VZ, then the diode is off. And when VSS is greater than VZ, the diode turns on. exactly the same as a regular diode in forward bias, right? A diode in forward bias will hold the voltage across it nearly constant at 0.6 or 0.7, okay, in the first quadrant. But a Zener is almost like a straight line. With a forward bias diode, you still have a slope. Zener diodes are manufactured to have a nearly constant slope, and that is part of the manufacturing process. Okay. If you take BMed 434 micro nano fabrication, where we actually fabricate our own diodes in the clean room, I think it's building. Can't remember what the building is. It's engineering 3 or engineering 4 or something. Anyone seen the clean room on campus? Engineering 4, thank you. Up on the second floor. BMed 434, it's cross-listed as EE 423. It's also cross-listed as MATE 434. And mechanical engineers do take it, MEs, materials, physics, chemistry. I even had biology majors once at U of L, where I was a grad student. So where we actually learn how to make these diodes. Anyway, coming back here, any questions? Okay. All right. So Zener diode characteristic is exclusively in the third quadrant, negative I, negative V. Third, 1, 2, 3, third. Yeah. No. Yeah. So minus V and minus I. And this is exaggerated. The slope is exaggerated. It's not typical. Okay, this is just for explanation purposes. More often than not, it is like a straight line like this. Okay, that's typical. Anyway, so you plot the load line. So this is the diode curve. It would either be given to you, or you would have an equation that would describe that curve. And the load line is plotted in exactly the same manner as we did for the forward bias diode analysis. We wrote out our equation. The equation is here. VSS is equal to VR plus VD. We plug in the values for the current and the voltage. Once you plug in the voltage and current values as 0, 0, you obtain the other coordinates and you plot the load line. So in this case, let's look at an example. Example is that the supply voltage is 15 volts, right? Supply voltage is 15 volts. What is your output voltage? V out. Okay, supply voltage is given to you. VSS is 15 volts. Calculate V out. So we would take our equation, and from here, from this equation, VSS is equal to ID, the diode current, times the resistor R plus the diode voltage. Okay. The diode voltage would also be our output voltage. So output voltage is the diode voltage VD. Both would be the same thing in this case because our output is taken across that regulator circuit. And so when VD is 0, ID is VSS over R, or RD in this case. And R, let's see, is given as 10 kilo ohms. No, 1 kilo ohm, sorry. 1 kilo ohm, 1000. So it'd be 15 divided by 1000. Gives me 15 milliamps. That would be the point right here. And of course, it's minus because it's in reverse bias. And when ID is 0, VD, of course, is equal to VSS, which is 15 volts, which is right here, minus 15 on the load line. Again, that minus simply indicates that it is a reverse bias Zener diode. That's all it means. It doesn't mean anything else. So far, so good? Yes. It was given in the problem statement. So these are the given values. Or provided values. So first example is basically when your supply voltage is 15 volts, your resistance is 1000 ohms. Calculate what your V out is. V out, of course, is the same as the diode voltage VD. We write a KVL expression for the circuit. We obtain supply voltage is equal to the resistor voltage plus the diode voltage. Plug in ID and VD as 0, and you find the two coordinates. You draw the load line. This is example 1, which is right here. And the intersection point is right here. And that intersection point tells me that my diode voltage VD at quiescent is minus 10 volts. Minus 10 volts. Now, obviously, the graph and the solution is already, the graph is already given to us, right? Otherwise, we would actually have to look at the graph and determine where that intersection point is. We have tools nowadays, software tools like Desmos, GeoGebra. You can plot all those points, and you can directly, the software itself will give us that intersection point coordinates. In the olden days, in my time, we'd have to manually plot out everything using a graph paper, engineering paper. And then once we have those plotted out, we have to like manually look at those values and figure out what the answer was. Okay, yes. So that is the intersection point right here. Intersection point on the graph. So that's the intersection point. And again, as I said, it's not, this is an example that's already provided, so we know the answer. But if we were to actually, if we didn't know anything, then we would plot out the diode curve and plot out the load line, either manually or on some software, and figure out what that intersection was. In this case, it's a solved example, so it's already giving it to us. But in the homework and in the quiz, we would be responsible to actually determining what that point would be. And then example 2 is basically if VSS would be 20 volts, which is the load line right here. Okay, load line right here. Then the operating point moves a little bit and you get 10.5 volts at the output. So again, the curve is exaggerated, but think about what it means. And I'll wrap this up in the next minute. Your input supply voltage is 15 volts. Your output is 10. Now your supply voltage jumped 5 volts, went from 15 to 20, but your output only went from 10 to 10.5. Okay, and even in that case, this is an exaggerated slope. Typically, it would be more of a flat line. If it's a flat line, no matter how much your input changes, your output would be constant. Instead of 10 and 10.5, it would be 10 and 10.01 perhaps, or just 10 and 10. It wouldn't change much at all. because your Zener diode characteristic would be almost a flat line. So then no matter what your load line is, it would remain constant at that operating point. And that would be the takeaway from this load line analysis. Okay, your input voltage VSS went from 15 to 20 volts. Your V out went only from 10 volts to 10.5. Okay, I'm not solving the second example, but you can see that you can see that solution right here. This is 10.5 and this is 10 volts. Okay. And with that, I'll end class here today. I apologize, I went 3 minutes over time. We'll end class here today. I will see you all on Monday. I'll bid you a good weekend. And Monday we'll have quiz number 2 related to Zener diodes. Okay. So there are some homework problems online, but it'll pretty much be very similar. The quiz would be very similar to the example I just did in class, as well as similar to the ideal diode problems. Okay. So if you have any questions, I'm still around for the next few minutes. For everyone else, I will see you all on Monday.